Right, yeah, yeah, yeah. So the end effect will always be there, even below the critical value.
Yes, but like I used 1 meter for entrance and exit lane, and their profiles are like totally different from the cells. So
Okay. But do you have net flow? No net flow still.
No, zero.
Yeah. There are lots of papers with net flow because this device has been used in.
So actually, that's how I know. For inlet and outlet, you get an answer.
Oh, okay. You have looked at the papers?
I saw some professors putting up YouTube videos about it.
Right.
So they
It's
have a flow,
yeah.
and they you can see that.
Right. So the idea is for blood separation, for plasma separation. You don't want the blood cells to stick to the wall. Okay, so you make one of them as porous walls, and you have blood flow in the axial direction, inflow and outflow, and then you gently spin one of them. So that creates a shear, leaves the cells away from that wall, and you can still separate the plasma through the porous media, so that you don't have this plugging in of that porous wall by the plasma cell. So that device, I think there are some papers that have appeared on that device. Yeah.
I still don't understand the first problem. So for the 1D solution, it's along the Z direction. If there's no cells, the velocity is all the same.
Velocity is all the same. No matter where you take the cut, it will always be the same.
So for the first problem the velocity is all the same.
Yep, that's correct. Yeah. Yeah. Okay, any other comments or questions? So you are okay with the pace of the course? Okay. Today I hope to finish the last concepts in averaging and simply look at the equations that are programmed in any of these software. It's COMSOL or Fluent or Star CCM. And from next lecture onwards, hopefully we'll move on to the numerical part. The second half of the course will be the numerical algorithms that are used to solve these equations. At least in simple cases, we will see the details of how to assemble the matrix. What do they mean when you're looking at the choices that you have for algorithmic parameters like over relaxation factor, under relaxation factor, etc. What do they mean? So we'll get an appreciation for those. How do I do this? Okay. So every lecture I try to capture what we did in the previous lecture, and those are the things that you should kind of review when we are going towards the end of the class. I said there will be a half an hour kind of oral exam. You should be able to discuss in a meaningful way the concepts that I have talked about and I have kind of highlighted here. So in the last lecture, we looked at the DNS method. Let me just make sure that it is recording. Yeah. So we saw the governing equations for the fluid domain and the governing equations for the rigid particle domain and how they interact without any approximation. That is the so-called direct numerical simulation of particulate flows. And similarly for two fluids that are immiscible, we saw that it's essentially the Navier-Stokes equation in both the domain. And so you can actually think of it as one field equation over the entire domain, but with discontinuity at the interface. And the interface can deform. And those are once again rigorously modeled using the Laplace pressure jump across the interface. So algorithms for these are being developed in the literature, but all of them haven't found a place in any of the simulators like COMSOL or Fluent. They will eventually in another decade or so. So those are the research tools that are used for understanding the multi-phase flow dynamics by direct numerical simulation. And then we talked about the random nature of the turbulent flows for single phase flow. So we are preparing ourselves for this concept of a time averaging and volume averaging because both turbulent flow and multiphase flow are extremely complex. And even though the secrets of their dynamics is hidden in the Navier-Stokes equation and the rigid body dynamics equation in the case of fluid particle systems, except for very idealized systems, we cannot get solutions. And so we need to, in a pragmatic sense, go through this idea of averaging. And this idea was proposed by Reynolds himself, who did these experiments of dye injection that we saw in the last class. And we saw the evolution of ideas briefly to leading up to the Kolmogorov universal scaling process, where we saw that the energy distributed against the wave number in turbulent flow has some sort of a universal behavior. That is, we inject energy on the large scale, small wave numbers. K is called the wave number. Think of it as the distance between peaks in your current assignment. In any periodic phenomena, in Fourier analysis, that's how you look at it. So you inject energy on the large scale with a turbine or a blade, and the energy is cascaded through a series of vortices and eventually dissipated and the so-called Kolmogorov length scale, the small scale, through molecular diffusion or dissipation. And that concept was developed, and the universal slope was developed by Kolmogorov using essentially dimensional argument. But they have been verified using direct numerical simulation of Navier-Stokes equation. And here I think the point that you made, when I increase the rotational speed 470, 490, eventually it blows up, right? Why does it blow up? Because the flow itself is unstable, and numerically it also manifests as instability. And we need to understand, once we start developing the numerical methods, what is the instability due to? Is it created by numerics or is it created by the physics? Okay,
so
the physics, yeah.
Regarding the same thing, so for COMSOL, if it's supposed to see the onset of turbulence also, I think you need to tick mark an option for turbulence, or else you won't even try to see whether it's going into turbulence.
Right, right. So I'm going to illustrate that today, hopefully. What does it mean when I check that box? This is basically what you need to get. Once you get that, when I tick a checkbox in Fluent or COMSOL, what does it mean? There is an underlying equation that tries to capture the essence of turbulent flow or essence of multiphase flow, right? And today's lecture is going to show you that link. How do we derive these equations? But the DNS, direct numerical simulation of turbulence, essentially means we just need to do the Navier-Stokes equation. Don't check that box. But I think, as you pointed out once, turbulent flows is inherently time dependent. So you have to enable time dependent solution. And then you need to refine the grid to death, right? Because you want to resolve very, very tiny, tiny vortices. Okay? So that is DNS. DNS is nothing but resolving the secrets for turbulent flow is hidden in Navier-Stokes equation. It's just that we cannot solve it analytically, even numerically. We need extremely large number of grid points to resolve the smallest high frequency fluctuations. And we saw experimentally that when you plot the velocity profile will have very high frequency oscillations. But the statistical behavior of that in terms of the histogram would be the same for two different realizations of the flow. But for a given realization, you will never be able to reconstruct the exact same trajectory because of the so-called turbulent features of the flow. And so that's what I'm saying here. It's difficult to resolve such high frequency and small spatial scale by DNS. And so we resort to time averaging. When you do time averaging, what happens to the Navier-Stokes equation and how is it modeled in COMSOL by checking that box, okay? But typically, if you don't have sufficient resolution and you just keep increasing your Reynolds number or Taylor number, you will find that it blows up, okay? So any questions? So this is what we started talking in the last class about the concept of averaging. Okay, so if I have a time signal like this, if I take the average of that, the average is 0. But if I square it and then take the average, I don't get that the average of the product that you see on the left-hand side. When I put an overbar, it means I'm averaging, okay? And the average is defined as, where do I have it? I have it in the previous one. I guess I don't have it. So the average is defined as average of any quantity, okay? So it's integral of some signal v of t dt 1 over delta t from 0 to t. That I'm going to call as V bar, or sometimes you will see this written as V within angle brackets. So that says it is an average quantity over a certain period of time, delta t, divided by delta t. And when I take that averaging on this function, essentially these two areas cancel out, so the average is 0. But if I take the average of this product, then I find that it's not 0. But the square of the average should be 0, because the average itself is 0, right? The square of the average is not 0, but the average of the product is not 0. So they are not the same. And it is this term that gives rise to so-called turbulence quantities, okay? And so this is the Navier-Stokes equation. As I said, it has the complete mystery of fluid mechanics in laminar flow, in turbulent flow, hidden in that, as long as it is a Newtonian fluid. The Newtonian fluid assumption comes here, which says that the relationship between the stress and the rate of strain is linear. So these are the properties of the averaging. Okay, so if I have a function phi and I split it into its average and perturbation, the lowercase phi is the perturbation about the average, and we saw this in a graphical form, something like this, right? So the perturbation would be this distance measured from the average, phi bar, okay? And so the average of the average is the average itself. It's kind of stating the obvious, right? Once I take the average, I have this line, and if I average it again, it's going to give me the same value, okay? But the average of the fluctuations from the mean, which is these vertical distances above and below, will cancel out. Okay, so that is how I define what my average is, right? So that this is it clear? Any questions on this? So the average of the perturbations is 0. Average of the average itself is the average. And if I take the
lambda prime,
pardon me?
that's separate symbols, right? One of the letter, right?
So I'm just taking two different functions and I'm doing the decomposition on both.
And I mean that 0, that something equals to 0, that's the fluctuation, right? Not the
That is the fluctuation from this. Similarly, there will be a fluctuation from this and also this, right? So these are the lowercase Greek letters are the fluctuating quantities. The uppercase Greek letters, this is phi and this is psi. Okay? So phi is the total signal which is decomposed into its mean and fluctuation. And psi is another signal. And these signals could be velocities, it could be two velocity components, it could be velocity and concentration, velocity and temperature, etc. And what we need to understand is when we go through this process, what happens to the Navier-Stokes equation, the energy equation, the mass balance equation, and which part contributes to advection, motion in a large scale mixing, and which part contributes to dispersion, that is fluctuations contributing to the dispersion. Okay, so here whenever I put a bar, that means I'm doing this integral operation that you see below, that is the averaging operation. Okay, so this is the averaging operation. Okay, so integral from minus 1/2 t0 to plus 1/2 t0 divided by t0. So I'm taking a signal of any quantity over a certain period of time and finding the area under the curve and dividing it by this so that I get the average. Now this is an integral operated on del dot v. So the overbar says the averaging is done on both the terms. But that will be the same as del dot v bar. So what I'm trying to do is I'm trying to develop a set of equations for the mean field, for the time averaged field. I'm interested in the time averaged quantity because the full quantity that is here is going to be very difficult to solve because I need extremely fine time resolution and spatial resolution. Okay, so getting back to this, what I'm illustrating here is if I have phi as some field quantity and psi as some field quantity, and I multiply by each by a scalar number a and b. A and b are constants. And then I'm taking the average. What does that mean? It simply means it is a times the average of phi plus b times the average of psi. Why is that? Because the integration is a linear operator. Okay? So this essentially means the over bar means I put an integral before that and integrate it over certain time. So that integration can be spread over the two terms because it's a summation term, right? Because it's a linear operation. Is that clear? Okay? And then the same thing applies to the derivative. Derivative is a linear operator. So when I say d phi dt bar, it means it's an average of this derivative. That means I'm replacing it by the integral. But integral and derivative can be switched around as long as the function is continuous. And so I can move that around and write it as the derivative of the average quantity. Same thing can be done for psi, phi or psi. They represent two different variables. But this is also true. Del phi is the same as del of phi bar, the average, the gradient of the average. Essentially, it says the average of the gradient is the same as the gradient of the average. But if I have the product of phi and psi, I am taking the average of that. That is not the same as the product of the averages, because I have an extra term. Where does the extra term come from? You need to substitute phi bar plus phi multiplied by psi bar plus psi. That's what this term is, right? So when I'm taking the average of that, that's what it means. Do you follow? When I'm taking the average of phi times psi, I'm substituting for phi here, I'm substituting for psi. So it is phi bar plus psi bar plus psi. It's a product of that. I'm taking the average. Okay? And when you expand it, you're going to get 4 terms. And the first term will give you this. The cross term between phi bar and psi bar and phi will be zeros. But it is a product between the perturbation phi and psi that's not going to be 0. That average operation remains as an unknown quantity. It is a correlation between the fluctuating components phi and psi. That's not 0. Okay, it's like squaring two random signals, and then averaging it. Okay, and this, when you replace phi and psi with two velocity components, u and v, they are called the velocity correlations. That is the Reynolds stress term. This idea was done by Reynolds.
What if phi and psi are the same quantity?
You can have them to be the same.
What about the last term?
Which one? It would just be like if it is u prime, or u prime v prime, or u prime w prime. If these are the 3 velocity perturbations, all it says is that there is fluctuation in the u prime component, but it is correlated with u prime component itself. And when you take the product of that, it's not going to be 0. When you take the average of that, it will be a non-zero term. And this would be one component of the Reynolds stress. Okay? So, and if you have u prime with t prime or u prime with c prime, those will be called the Reynolds flux terms. This is velocity fluctuations correlating with temperature fluctuations at the same point, same physical point with time. Do you follow that? Is that your
That last point is hard to understand. U prime, T prime, what was that about with respect to point you were saying?
Well, imagine that you have a flow, okay? Flow past a cylinder as an example. And you are in the turbulent regime, meaning Reynolds number past this sphere is 10,000. So you have a lot of the vortices on the back side of it. And you put a probe, and you measure with that probe temperature with a thermocouple. And at the same point, you put another probe that measures the velocity component, hot wire anemometer. Will give you the velocity fluctuations. So you get 2 signals, one for u and one for t. Okay, and those signals are going to be something like this: U prime and T prime. So all this says is that I'm going to take the product of these two signals to define a new term, which is U prime T prime, and then I'm going to average them out. And that average is not going to be 0, but it is that average that gives you enhanced mixing in temperature. So if I have to homogenize a hot fluid in turbulent flow, the moment I increase U prime, I will be able to achieve greater mixing. Okay? Same thing with concentration. So if I put a dye at a particular point, how fast will that dye mix into the neighboring part? If the flow is stagnant, it's only molecular diffusion that's going to diffuse it. If I have a slow advection, the dye may be carried around, but if I reverse that, it will go back to the same position. In fact, you've seen that, right, in one of the earlier videos. But if I have fluctuations that are irreversible, then that fluctuating velocity will carry the dye and make the dye diffuse much more quickly. That is what is called turbulent dispersion. Okay? So what we are going to do is, after we apply these ideas of averaging to the Navier-Stokes equation, we will get a term that will involve such correlations that we have written down. We don't know what they are because our sensors give us only the mean field. So what is the difference, for example, if I'm measuring the velocity at a particular point with a hot wire anemometer, I will get a signal like this because hot wire anemometer is a very high accurate device. If I put a pitot tube, what do I get? Do you know what a pitot tube is, right? What do I get at a pitot tube? Its inertia is so large it cannot track all the fluctuations. You will get a mean velocity. Okay? So the probe that you use should be sensitive enough to track the high frequency fluctuations. Turbulence made great strides only after hot wire anemometer was invented in the early 1900s. So, and then laser Doppler anemometer came. Now we have PIV, all kinds of good experimental data to probe turbulent flow structures. Any other questions? Yeah.
The part like sidebar fire, firebar,
How did-
side or opposite?
Which one?
The other terms.
The other terms, when you average them, would be 0. Why? Because if I take, for example, phi bar with psi, let me erase that. So I have this term with this as a possibility, right? So phi bar times psi, average of that. Okay, but this is already an average, right? So I can take that out. So that is the same as phi bar multiplied by psi bar. Okay, but psi bar is 0. Right, the average of it is the average of the product of these not 0. Average of the fluctuation. That is only the fluctuating components. The average of that is 0. Okay. Any other questions?
Excuse me.
Yeah.
Is the derivative of fluctuation has some physical meanings? In static, they predict the heat capacity by fluctuation in energy. Is it
Yeah, you can relate it to kinetic energy, the fluctuations. In fact, there is something called K epsilon model for turbulent flows, which is K is the kinetic energy of the fluctuating components, right? So U prime plus V prime plus W prime are fluctuating correlations of U with U itself, right? So some of that is called the kinetic energy of turbulence, right? So is that what you mean?
I mean that is it like coefficient that you can get from taking the derivative of fluctuations? That's what they do for like getting.
I'm not very knowledgeable in StatMech. Okay. In fact, you know that because I sat through a course from Cheng Wong on that. So I don't know how to relate this to your experience with StatMech because I'm not familiar with StatMech. What do they do? But I mean, I'm trying to learn about MD, and I see that some similarities between MD and DEM. In fact, so much so that the MD code lights is being used for DEM also, right? So you get these fluctuating velocities of these particles, and you relate them as kinetic energy of the particles, but are they related to any material property? That's what you're asking. Gradients of these fluctuations are related to some material properties like heat capacity, right? So that's a way of upscaling information for me, because what happens at the molecular scale with these fluctuations is related to the ability to store energy perhaps, right? And so I have seen this being done with predicting viscosity. So what you do is at the molecular scale, you take these fluctuations in the molecular velocities, and these are related to the stress. And so proportionality coefficient is your viscosity. So molecular viscosity, thermal conductivity, diffusivity, they can all be predicted from MD type of simulations from these fluctuations. Now, if you ask the question, can these correlations, derivatives of these correlations, be related to a material property like that? The answer is no, because these depend on the flow field, U prime and V prime. Okay, so what you do is you do exactly like what you do in the molecular case, where you say that the heat flux, for example, is minus K times gradient of T, right? So that defines your thermal conductivity. So you propose a similar model, called a Bosnisk model, for example, which introduces a turbulent diffusivity, a turbulent heat diffusivity, a turbulent mass diffusivity. But unfortunate thing is these are not properties of the material. These are properties of the flow. And that's where the challenge remains in turbulent flow. Because if you measure them or if you predict them in one case, you cannot use it universally in other cases. So you have to build models for each type of flow pattern. And this is why turbulence modeling gets challenging and interesting. But a lot of advances have been made in turbulence modeling in predicting these fluctuating quantities. So we will see a few models of those. Good question. Any other comments? Okay. So this is the momentum equation. We are applying the averaging, which means we are just applying this operator in front of the entire Navier-Stokes equation. First thing we apply is that it can be transferred inside term by term. So the average of the first term, average of the second term, nothing fluctuates there. Rho is constant, G is constant. P can fluctuate, so the averaging of that and the averaging of this. Okay? And then you take that inside the derivative, this averaging inside the derivative, and recognize rho is a constant. So you get a term only in terms of the mean velocities. Remember, the mean velocities are the time average velocities that give you the large scale motion, that gives you advection. Here is a problem. When you take this averaging inside, you can take it inside the derivative, you can take it beyond the rho, but this correlation will exist. And that is a dyadic product between two velocities. So this is actually a tensor, 9 components. That is U prime with U prime, U prime with V prime, U prime with W prime, V prime with U prime, V prime with V prime, etc. So you'll have a 3 by 3 matrix that represents these fluctuations. And this can be taken inside because it's a linear term, this can be taken inside. So you see that the harmless terms are all the linear terms. When you're doing the averaging, you get the same equation as before.
Is that the Reynolds stress tensor?
This is the total stress. Now you need to split this into 2 parts and you will get the Reynolds stress.
Okay.
Because this is still, this is the full velocity.
Okay, that's not.
These are all the time average quantities, but this is still the full velocity.
Okay.
So here I'm showing what happens to the term. Okay, so the V is written as V bar plus V prime twice, and then average. And when you do this, is exactly what we did with phi and psi before. You will get the product of the 2 averages, and then the remaining 2 products, when you apply the average on that, will be 0. And then this is the term that is not 0. The last term is your Reynolds stress terms. Okay, so this is the culprit. Okay, the nonlinear term in the Navier-Stokes equation is the culprit for generating turbulent flows. Okay, and they are extremely good in terms of dispersing mass, momentum, and energy. Okay, so they enhance heat transfer, they enhance mass transfer, etc. But they enhance momentum transfer, but what that means is increased pressure loss, increased energy loss. Okay, so increased heat and mass transfer, process intensification, that's the idea. You need to intensify, you need to make this term as big as possible. So you bring the molecules together much more frequently so that they can react or they can separate or mix or whatever. Okay, so these terms would be 0. And so the Navier-Stokes equation, what happened to it, becomes this. This is exactly as before. This is, there is a slight space there. I don't know whether you can see it. This is actually rho B bar times V bar. It's not the average of both. These are the time average quantities, mean field equation. So if every term is in terms of the mean field, then the equation is closed. You can solve the problem. But here, we have these fluctuating quantities that is not 0. It's called the Reynolds stress, and when we expand it, it has these 9 terms. These are all correlations of one velocity component with another velocity component. Okay? And the sum of the diagonal is what you will call as the turbulent kinetic energy. If you sum them all up, that is represented as the turbulent kinetic energy. To construct what the last term looks like, you can do it with DNS. That is, go back to the Navier-Stokes equation, don't do the averaging, but resolve it using time-dependent, very fine grid. You will be able to get these fluctuating components, and then you can actually calculate that. Okay, each one of these two, the 9 terms. What do you notice about that? They are symmetric, right? Because V1 prime, V2 prime is the same as V2 prime, V1 prime. So that stress tensor is symmetric. So there are 6 components that are unknown. What is our challenge? Our challenge is to write them as some function of V bar. If we can write them as some function of V bar, then this equation will have only V bar, and we can solve that together with the continuity equation. Okay? And that is called the closure problem in turbulence. How do we relate these fluctuating components to the mean velocities? Turbulence modeling is a whole course can be given on that, is entirely about that problem, trying to identify this function.
Let's take a product of 2 fluctuating components. How can you write that as function of V bar?
Not easily, right? So what you do is you propose a model. So what does the model say? The model says, one model, I think I might have it here, simply says that this is what we do when we are ignorant, right? This is what we do. So you recognize all these terms are exactly the same. I wrote this V bar term as turbulent stress term. Okay? And that turbulent stress term is modeled by this. Sorry, not here. This is the laminar one. The laminar relationship is between the stress and the rate of strain is linear. That is Newtonian fluid. It is a material property. The viscosity is a material property. That is this term. Okay? But I propose that there is a turbulent stress term. It's called the turbulent stress. That is the fluctuations between the correlations between 2 fluctuating components is called the turbulent stress. And I say that is proportional to the gradient of the mean velocity. You can question why. And there is really no good answer. Bozenius came up with this model, inspired by what we know here, and said, "This is I'm going to call this as a turbulent viscosity." Okay, but turbulent viscosity is not a material property; it is a function of the flow field. Okay, but in most of the models that we use, we make that approximation, that assumption, that the turbulent stress is linearly related to the mean gradients of the mean velocity field. Inspired by this, but you can ask the question, what makes you think that this is a good model in stress and rate of strain? We already know Non-Newtonian fluids don't obey that, right? So, but any material that obeys this is called a Newtonian, and this is a property I can measure in a viscometer, and I can use it in any other flow configuration. By changing the flow configuration, this property doesn't change. But if I propose something like this is a one-dimensional version of yx component, so dvx dy. But if you generalize this, you will have exactly the same thing, except this will be bars, and this will be the turbulent viscosity. But that turbulent viscosity cannot be measured in an experiment unless you measure the fluctuating components and correlate that.
So as you said, the turbulent viscosity is not a material property.
It is not a material property. It is a function of the flow condition. So if I measure it in one device, I cannot use it in another device.
Is it a statistical value, like averaged over a range?
Well, this is a model that this is a true unknown that we have in the
No.
average.
The reason I'm asking is because you said that it's a function of the flow field, and
Yeah.
the flow field is basically eddies. In the
Is eddies, yeah.
Different sizes and different
Right,
velocities.
exactly.
So in one whole tube, you'll have different modes.
Yeah.
So this is like the origin of large eddy simulation.
Well, the large eddy simulation, we will talk briefly about it, makes essentially similar assumption. But it says I can resolve all the eddies larger than my grid scale. And anything that happens below the grid scale, I'm going to put an eddy viscosity concept. So it is embedded in the eddy viscosity concept at the smallest scales. Okay? And if you keep refining the grid, the large eddy simulation will approach DMS because the contribution coming from the modeled part is much smaller and smaller. It depends on the grid size. Whereas in K epsilon model, you just have a field equation for K, the turbulent kinetic energy, and epsilon, the viscous dissipation rate in the turbulent flow. So there are two nonlinear PDEs that you need to solve for the K epsilon model. And once you get your K and epsilon, you have a relationship to calculate this mu t. Mu t locally at every point in the flow. Okay?
So my question is,
Yeah.
What's the use of this model if it's changing point to point?
Well, that is the reality, right? So the engineering approach to answer that question is, since I cannot get a universally valid closure model relationship relating the fluctuating components to the mean, I propose this model, but I devise a model that will allow me to calculate it from point to point depending on the local flow field itself. So I have another set of equations that drives what the value of this mu t is from point to point locally. Okay? And of course, that model has a number of parameters, 9 constants, and they have been tuned by very careful experimentation against the so-called grid turbulence that I showed you in the last class, turbulence behind a grid under homogeneous condition. So the K epsilon model does very well when you have so-called homogeneous turbulence. What is homogeneous turbulence? Something that we should also talk about. Okay? So if the magnitude of the fluctuating components are all the same, that is, fluctuation in one direction is the same as fluctuation in the other direction and the third direction, then I call that as an isotropic homogeneous turbulence. Homogeneity means from point to point, isotropic means directions. So the fluctuations are all the same in all the directions. But that cannot be true when I'm approaching a wall. Why? As I approach a wall, the velocity goes to 0, right? So the fluctuating components will decay. And so the flow is highly heterogeneous as you approach a wall. And that is why the K epsilon model will fail near the wall. And in most of their packages, including COMSOL, they have something called the law of the wall, which is based on experimental data. The experimental data shows that there is a universality in the way that these fluctuating components die as they approach a wall. This is the logarithmic law of the wall. You would have seen it in undergraduate fluid mechanics course, U plus equals Y plus, or U plus equals log Y plus, etc. Okay? So that's an algebraic expression that says how does the velocity field change near the wall. And that has been patched into these simulators as the boundary condition for the wall. boundary condition for what? For the turbulent flow equations.
You know how they do perturbations to find the inner region solution and the outer?
That's the basic idea. So you have this idea of boundary layer, the laminar sublayer, and then so you're taking the solution from zero velocity through the laminar sublayer, through the intermediate layer, and the fully developed turbulent flow. So you patch it with inner solution and outer solution. Yeah. And you do it computationally. So this data essentially shows the nature of the heterogeneity. So this is experimental data from automated anemometer for Bx prime, Bx prime. This is flow in a pipe. Okay. So Z is the axial velocity. So Vx, Vz. Okay. And then Vx, Vz. And you see that the fluctuations die down. Okay. But they are very large in the middle, and they are homogeneous in the sense, if you watch carefully, fluctuations in the x direction, that is perpendicular to the flow in a pipe, and this is in the direction of the flow. They both approach each other in the core of this. This is the center of the pipe, this is the wall of the pipe. So the fluctuations approach zero near the wall, and the fluctuations approach each other. So the core is subject to homogeneous isotropic turbulence. But as you go away, it is not. Near the wall, you'll find that they are quite different. The fluctuations in the transverse direction is very different from the fluctuations in the axial direction. Okay? So it is these experimental measurements that inform us on how to build these models. Until this was available, until automated anemometer was available, we could understand the nature of the turbulent flow in general. So they added a lot to our understanding, and then the model building started. Any questions? Okay. So I guess I should have injected the K epsilon model at this stage, but I'm switching topic to talk about averaging in a different sense. Okay. So what we have talked about so far is averaging of the Navier-Stokes equation in the time domain to take care of turbulent flow evolution. Okay. The next thing is the random fluctuations in space. Yeah, sorry.
That's something before you started. Like, so you said DNS doesn't capture this properly, so what?
No. DNS, in principle, will give you all the information about these fluctuating quantities. These fluctuating quantities that you see here, you can calculate from DNS. But what you need is extremely powerful computers, because you need extremely small grid to resolve the tiny vortices, and then very small time step to resolve the high frequency fluctuations. If you have that data, then after you get the data, you do the time averaging on the data to get the fluctuating components of each component, and then you can take the correlations. Okay, so that will give you what these data look like, but it is our job still to represent that data in the form of an equation so that we can put it into the time averaged equations.
So this K epsilon is still a part of DNS.
K epsilon is not part of DNS. K epsilon is, maybe I think we should probably switch to what the mystery about K epsilon is. So let me do that. I think I have the notes somewhere else. So far what we have, the thought process is turbulent flow is complicated because of large scales of fluctuations in both space and time. So we're going to do the time averaging to get equations for the mean component, and then we isolate the unknown in terms of the fluctuations. And the fluctuations are modeled in the form of the so-called Bozenisk equation. Okay, that is, the fluctuating components are related to the gradients of the mean velocities through a turbulent viscosity term. Okay, how are these turbulent viscosity terms modeled? So let me answer that question, and then we'll come back to multiphase flow. Yeah.
So, like, have they verified that assumption or that equation, like using like you said, once you
That's a very good question. Have you verified this proposal that the fluctuations are linearly related to gradient of the mean field? Has this equation been verified? That's your question, right? This equation has been verified for many materials, and we know which materials don't obey that, right? But in this situation, we know certain flows do not obey that. Okay, and these are flows, swirling flows, highly anisotropic materials. You don't find this equation to hold good. Okay, but there are so many parameters in there that they have been carefully tuned that it is applicable to a large class of industrial flows, pipe flows, expanding flows in fluidized bed and stuff like that. They are not bad. They do a reasonably good job. But it is a model. There is error associated with this model because we don't know how exactly to make it rigorous. In this case, there is no uncertainty. Once I measured my viscosity as accurately as possible, I know that is a good model. In this case, I will never know that it is a good model or not.
So it's like a correlation with different.
It's a correlation. It is a curve fitting exercise. But you need to see how complicated the curve fitting is. It's not simply an algebraic equation. Okay? And it is that mystery I think I need to remove. Let me see whether I can find in a different place. I have no idea where it is. I need to open several files. Yeah. No, this is time averaging. Yeah, this one would do, I think. So this is the equations taken directly from Fluent. Okay, and what you see here is this is the time averaged term, the advection term, the transient term, and here you have the turbulent stresses. Okay, and he also shows in answers when you do the same operation on energy balance equation, you get these fluctuations between the velocity and enthalpy, which can be changed into correlations between velocities and temperature profiles. And that is modeled through the gradient, which is what I guess you were referring to, gradient of the mean temperature, introducing a parameter there. This parameter in the molecular case would be specific heat, but here it is a parameter that depends on the flow condition. Okay? And same thing is done in here. Yeah, this one. So this would be the time average quantities, but this is not a property. This is the turbulent viscosity. Okay? And so there are about 10 different turbulence models in ANSYS. Okay? So one of the turbulent models simply says the derivative term has a molecular viscosity plus the turbulent viscosity, because I have used the same linear relationship. So the effect of that is essentially this asset the molecular viscosity is modified by the turbulent viscosity due to these fluctuations. But this is a property, this is not. So I can just write an algebraic equation that relates this to the mean velocity. And that is called the Slarard-Almaraz model. So essentially, it's the same equation that you're solving, it's only slightly complicated because you have an algebraic equation. But it's a terrible model because you cannot use it in every flow situation. But it is available as an option in COMSOL, I think, as well as in Fluent. Okay. So the next model is one that tries to relate this turbulent viscosity through a function that is given here. So these are all highly empirical. Everything is fitted. There are a number of parameters that are there. But in one approach, you say that it is related to vortices, and vortices are the curl of the velocity gradient. Those are the ones that give you a sense of the magnitude of the rotation. Okay. So this is the Spallard Almiraz model still, and that has a number of model constants. These are all intently tuned against some experimental data. But let me just go to the K epsilon model. So this is how the K epsilon model looks. Can you derive that in an ad hoc sense? So you can actually derive an equation for these u prime, v prime from the Navier-Stokes equation, and then take the diagonal terms and add them up, you will get this so-called K equation. K is the kinetic energy. So it is a quantity that is a field variable, depends on time and position. It is affected by this velocity in the same way any other quantity is affected. So it is a turbulent kinetic energy that is moving around in the flow. So it varies from point to point. And it is also dependent on this turbulent viscosity. Okay. And there are terms that model the production of the kinetic energy, which happens near the wall. And this is due to the buoyancy-driven turbulent kinetic energy production. And there are distractions of the kinetic energy as well. And similarly, you have an equation that is written down for so-called energy dissipation rate. How much of energy is dissipated per unit volume? So that is the epsilon quantity. So there are two equations. Those are field equations, meaning they are functions of x and t, and they are partial differential equations. They themselves depend on this mu t. They have exactly the same form as the Navier-Stokes equation itself, an advection term, a diffusion term, source terms, production. And this is the reason for why these simulators have become very successful, because if you write one algorithm, one routine that knows how to solve this template of an equation, by simply plugging various values here, whether it is k or epsilon or u1 or u2 or u3 or concentration or temperature, you just recall and use the same routine. So it's very easy to generalize these solvers for so-called 1D physics. Okay? But after calculating this k and epsilon at every point in a flow domain, you calculate the so-called turbulent viscosity. That is what removes the mystery. This turbulent viscosity is given as rho times c mu times k squared over epsilon. K and epsilon come from those two equations, partial differential equations. So at every point you calculate the k and epsilon, plug it in here. At every point you get your turbulent viscosity. Plug that into your mean field equation. Okay? And this equation, as you would notice, has a number of parameters as well. They are all fitted against experimental data. Okay, so where do these parameters appear? So you can see it. Okay. C1 epsilon, C2 epsilon, sigma epsilon, sigma k, etc. They are all parameters that are empirically fitted.
So K and epsilon can be visualized as something that we use to compute the turbulent viscosity.
They are used to compute the turbulent viscosity from this equation that you see here.
And they plug it back into
And those are plugged back into the time averaged Navier-Stokes equation here. Okay. So now what you have is you have 3 momentum and 1 continuity equation. They are all for time averaged quantities. And then you have a K equation and an epsilon equation. It's called a 2 equation model for turbulence. So you're solving 4 plus 2, 6 equations. And they are coupled. So the K epsilon feeds this turbulent viscosity term that you have here. Okay. Now, when you have LES, what do? You still have the same hypothesis that the fluctuations are related to the gradient of the mean, but that viscosity that you put is restricted to the grid scale. Okay, so that viscosity will go to 0 as the grid scale is refined smaller and smaller. And
viscosity goes to 0?
if that term goes to 0, if the viscosity is made grid dependent, and if the grid goes to 0, that viscosity goes to 0. That is the turbulent viscosity, remember that. So the turbulent viscosity goes to 0. That means this entire term that you have added through the time averaging goes to 0. That means you are recovering full DNS solutions.
So as you solve smaller and smaller, I mean, as our dimensions get smaller, it gets basically approaches DNS.
It approaches DNS, exactly right. Yeah, you can think of it that way. Yeah. Yeah. So what is the lesson from all this? That the mean field gives you the large-scale mixing, large-scale advection of energy, mass, momentum, and the fluctuating components gives you the small scale. So in reaction engineering, that you have done reaction engineering course, you would have learned macro mixing and micro mixing, right? Macro mixing is governed by the advection term. So very, very important to get the time average velocity field for that. Micro mixing is determined by the turbulent dispersion term. It's important to get the correlations correct for that. Okay? So any questions? Okay. So that's the kind of a door open for understanding at a conceptual level what turbulence modeling is about. Okay, that turbulence is a complicated velocity field with fluctuations. We decompose them and we model the correlations and the fluctuations through a variety of models, and there are many, many different models available. And the similar problem arises when you're dealing with highly complicated multi-phase flows through porous media, where the geometry is so complicated, only statistical description makes sense. Or when you have mixtures like these that are highly spatially dispersed. So we introduced this idea of a volume averaging instead of time averaging. This picture illustrates what a volume averaging is. So if you think of the blue as water and red as oil droplets, DNS of this will try to track where the interface is of every droplet, whether they're coilless or breakup, etc. We have seen what those equations are. These are just Navier-Stokes equations solved directly, imposing the interface coupling condition. But in a volume averaged equation, there is a whole class of important models called two-fluid model or Euler model. What is the idea that goes behind that? And that, I believe, is the main tool used for studying industrial scale problems, because DNS is going to be impossible if you have more than 20,000 particles or 20,000 bubbles or droplets. So this smoothing has to be done, and that means, once again, we will have closure relationships. We need to understand where they come from. So if I take a yellow dot that you see here as the representative elemental volume, I can place a center on that, and at that center point, I can define an average value for all the reds. What fraction of that yellow dot consists of red, oil droplet? What fraction consists of blue, the water? So I can assign alpha of oil and alpha for water. At that particular point, the center red dot representing the center of that yellow circle. Okay? So this model is called the interpenetrating continua model. The reason is, at the same physical point, I have two values for the field variable volume fraction. This is the volume fraction of oil, volume fraction of water. Do you follow that idea? Okay. So if you want to, I guess I have another slide somewhere. Yeah. If you want to take this, for example, if I draw a circle and I put a center there, I can carry out the integration of all solid volumes inside that circle and express it as a fraction of the total volume. That will be the volume fraction of the solid at that particular point. Similarly, I can add all the empty spaces and divide it by the total volume. That will be the volume fraction of the beta phase, the gas phase, in a porous medium, right? So I have porosity for the gas phase and porosity for the solid phase. But I can move this representative element volume ever so slightly to the next point. I can do the same job again. And I will get two values for volume fraction of the solid and the gas at the next point. So I'm treating these average values as continuous variables in space. Okay, and that is why it's called interpenetrating continua, because at every point it is as if I have both phases coexisting, but they don't. They cannot coexist. DNS would resolve. DNS would say, I'm going to solve only the flow in the empty space for the gas or the liquid. The solid is fixed, right? If it is a fluidized bed, these solids can be moving around. But the concept is still the same. I can do an averaging using a probe that is larger than the dispersed space, but it is smaller than the equipment scale, so that I get a sense of how the volume fraction of each phase changes from point to point within that vessel. Do you understand the idea? Any questions on that? Okay. So if my LO circle is 5 pixels, for example, and I do this by scanning point by point, I get an image like this. So I get a blurry image. Why? Because when I'm on the edge of one red dot, I'm smoothing. Okay, so I don't get a very clear definition of that. If I make it 10 pixels, 25 pixels, 50 pixels, it gets blurrier and blurrier. But still I'm able to say that this region is rich in red, that region is rich in blue. And that is the extent to which a two-fluid model can predict the distribution of phases, the distribution of velocities. I can apply this concept to any quantity. I can apply it to pressure, I can apply it to velocities, I can apply it to density, etc. Okay? That idea of a volume averaging. The volume averaging is to take into account the heterogeneous distribution of phases in space. Okay, so the key condition is my representative elemental volume that you see here, R0, must be much smaller than the equipment scale L. So this diameter must be smaller than this. Okay? But it must be much larger than the diameter of the dispersed phase. Because if it becomes smaller than that, then I will see only one phase or the other phase. Okay? So this has important consequences in validating your model against measurements, right? Because what you're predicting is some sort of an averaged velocity for each phase. And what are you going to measure? What is your probe going to measure? Is it going to measure on the same scale? Is an important question. Okay, any questions on that? I think you are all familiar with Darcy's law. Darcy basically discovered this empirical relationship between flow rate and pressure gradient, and he defined a new material property for the porous medium called the permeability. But this equation has been subsequently derived from the Navier-Stokes equation through this concept of volume averaging that was introduced by a series of chemical engineers, Whittaker, Slattery, and Jackson. So they have developed this whole set of equations derived from Navier-Stokes equation that are applicable to fluidized bed, to porous media flows, etc. But essentially this equation is embedded in the Navier-Stokes equation in some sense. So if you solve this directly from Navier-Stokes equation, you should be able to predict what the permeability of a given porous medium is. By even using Lattice-Boltzmann, you should be able to back calculate or extract. This is the upscaling information. Typically, we would want to solve only the Darcy's law for the filtered equations or the averaged velocities. Okay? But you need K as a parameter because this model is parameterized with the permeability. But Navier-Stokes equation is not. So if you solve the Navier-Stokes equation through a complex porous geometry, you should be able to actually calculate what this is. If you do it in two fluids with full resolved DNS, you should be able to predict what the relative permeability is. This is for those that are from petroleum engineering, you know what these concepts are. So this was, as I said, Whittaker's analysis is this. It was derived in the 60s. So he took, this is not the Navier-Stokes equation. What is that equation? It is the Stokes equation. Navier is lost. In the sense, the inertia term has been thrown out because the flow field in porous media is always very slow, creeping through. So inertia is not important. So he started with these two equations, continuity equation and the Stokes equation, applied this concept of that volume averaging, and derived this is how you define what the volume averaging is. It's essentially the same operator like time averaging. Take any variable, integrate it over a volume, divide by that volume, and call that as your average variable. So you apply this operation on the Navier-Stokes equation term by term. Okay? So there are two kinds of averages that are defined. One is when you divide by the whole volume. The other one is you divide only by the volume of that phase. What is the difference between those? Do you know the difference between superficial velocity and interstitial velocity that you would have seen? One is a superficial velocity, the other one is an interstitial velocity. Which one is superficial velocity? The first one will be equivalent to the superficial velocity. That is, you have a flow rate in the packed column divided by the total area. That gives you the superficial velocity. It is a velocity you will find nowhere because the fluid is actually going through the pores and it has less area to flow through. Its velocity will always be higher. So this would be the velocity that is characteristic of the true velocity in the interstices. But two definitions are used, so he starts with defining both, and the relationship between the superficial velocity and the interstitial velocity is simply the porosity. Okay? So if you take the interstitial velocity and multiply it by porosity, that gives you the superficial velocity here. And this is the math behind it. So he derived something called an averaging theorem. Remember, we said when you have an integral over the derivative, we could switch. Okay? And that idea doesn't really work out in volume averaging. If I take the average of the gradient of a function, is not the same as gradient of the average. There is an additional term that comes from Reynolds transport theorem, Gauss divergence theorem. It's essentially a calculus quantity. Right? But this is an important term, and this is the closure that we need to worry about in volume averaging. Because what it has is the quantity that we are evaluating on the interface, because it's a surface integral over the interface between the two faces. So that captures all the interface transfer mechanism. So if I have a particle like this, the integration is over that particle. And it may be stress, it may be drag, it may be interface diffusion of the material if something is dissolving. It can be diffusion of heat if the particle is heated and the gas is not, or the liquid is not. So all those terms are captured or lost. In order to be able to calculate them, I need to know in a fully resolved sense what the variable psi is. It could be velocities or temperatures or concentrations. DMS once again will give you that. But if you volume average it, if you're dealing with these equations, you don't have information on that. So you need to propose a closure relationship. And that closure relationship is the so-called drag loss, lift coefficient loss, etc., that you will find. And it's not very difficult to see that when you apply this to the continuity equation nothing but del dot V beta, average of that, is the same as gradient of the average plus this quantity. But if it is porous media, this velocity on the solid interface is 0. So this term drops out. And the volume average, maybe the continuity equation looks exactly like the fully resolved continuity equation. Same thing happened with the turbulence model. Okay? But the momentum equation, that is the first equation here, when you apply the volume averaging, you get the volume average pressure and you get the volume averaged viscous term, and then you get this integral. This integral is the stress evaluated on the interface. So that is precisely the drag, form drag and skin drag, pressure force and the shear force acting on the interface between the two fluids. And that we don't know until we fully resolve it. So we just close that. So these are the closure models. And the closure for Darcy's law is introduce your K. permeability. And he shows rigorously that K is actually a tensor, meaning that the drag or the resistance is directionally dependent. So if you have, for example, lamellar structures of porous media, it may have high permeability in one direction and low permeability in the other direction. And so it is actually a property of the porous medium, but it is not isotropic. If it is isotropic, if the porous medium is isotropic, made up of spheres, then this is a scalar quantity. Otherwise, it is a tensorial quantity. But that is your drastic sum. Comes from Navier-Stokes equation through a careful argument. And Whittaker has an entire book devoted on volume averaging. Okay, I'm just taking some basic ideas from there to show you what is the important message that you should get, that you should understand what volume averaging is, what are the consequences of volume averaging, losing of information, and what you are getting for the average quantity or averaged over a certain volume, and you need a closure relationship. The closure relationships capture the interaction between the two phases. Okay, this is the forces exerted by the solid on the liquid or the solid on the gas, etc. Any questions? So this is the that argument when you apply it to the full Navier-Stokes equation. We saw for porous media earlier. When you apply it to the full Navier-Stokes equation, gives rise to these volume average momentum equation, volume average continuity equation. And this chart taken from the book by Ishii talks about this two-fluid model. So the two-fluid model essentially says, I have a momentum equation for each phase, but it is smoothed, averaged over the volume. So I will have very similar terms. If you see here, the continuity equation looks like this for each phase. Okay? And here alpha k is the volume fraction for each phase. And this is the velocity, volume average velocity for each phase. K is the subscript for the phase. And this is the momentum equation. And you see that it looks exactly the same as single phase equation, except each term gets multiplied by the volume fraction. And there are two such equations, one for each phase, if there are only two phases. If you have three phases, we just use three copies of these three equations. And this is the pressure term, this is the viscous term, this is the gravity term, and then this is the magic term that contains all our ignorance coming from volume averaging. So that you need to model. And Fluent and COMSOL will give you lots of options for drag models, which is interaction between the two phases, interaction of forces. This is a momentum equation. Similarly, when you have a mass balance equation, how will it change? Instead of Vk, you will have C. One of them will be V, the other one will be C. And this will be in terms of gradients of C. This will be the diffuse model. And that will be an interface mass transfer coefficient instead of interface momentum transfer coefficient. Okay? Any questions? So that is a very good book to read about the two-fluid model. Fairly difficult in terms of mathematics involved in that, but he goes through the mathematics and the physics very nicely, and he has done a lot of work, published a lot of papers, is really an expert in that area. So essentially, at the end, you end up with one macroscopic momentum equation for each phase, phase 1 and phase 2, and then the interfacial conditions are borrowed. Okay, so I think that's basically what I wanted to talk about, the idea of volume averaging and time averaging and the equations. We will see in COMSOL how these equations are laid out and how we access them. So when you check, for example, K epsilon model, what happens in COMSOL. But then from the next class, I want to start dealing with algebraic equations, linear and nonlinear, and then moving on to discretization of the differential equations. So the rest of the course is on the numerics of how do we solve these model equations, so that you get some idea of what is finite difference, what is finite element, what is finite volume, etc. Okay, any questions? Yeah, I'm going to introduce essentially using simple ordinary differential equations. What is the idea behind finite element method? So once you grasp the idea, to implement it in 3 dimensions is a lot of programming. But conceptually, you would understand what is a finite element method. What is
That's
it?
for solids, right?
Hmm?
Finite element is for solids.
No. It's used for fluid mechanics. COMSOL is a finite element code. It is used for any.
Volume was for fluids.
Hmm?
I thought finite volume was for fluids and finite element.
No. It's those misconceptions that you can dispel with this course, hopefully, right? The modeling is driven by physics. The solutions is driven by numerics. You can apply any of the 3 methods, finite difference. In fact, more methods are there: collocation methods, spectral methods, etc. So all these methods can be applied to solve any of these partial differential equations. But the way that historically things have evolved, Fluent used finite volume method, Open Foam used finite volume method, COMSOL started with finite element method. Very few codes that do finite difference, because finite difference, you will see, has difficulty dealing with complicated geometry. Unstructured meshes are more difficult. Whereas in finite element, that's handled very elegantly. So I will show you why finite element is better suited for that. And finite volume method has been a kind of a compromise between finite difference and finite element to accomplish the same task of handling complicated geometries. So we will explore those ideas using initially ordinary differential equations, and then maybe PDEs in 1 dimension with time, etc. Okay, all right.